We are a startup in the Washington, D.C. area. We have a big idea. We basically want to fix the web itself. And this idea came because when we addressed some of the fundamental properties that we would all like to have on the web, like authenticity, confidentiality, and privacy, we realized that these are really foundational properties that if they're breached in any one place, anywhere across a distributed system, you just lose those properties for the whole system. So we very early on realized that these are problems that should be solved at the foundation, and that's what we set out to do. So as I mentioned, we are a startup in the DC area. Important to note that because of this big vision, we also incorporate the company as a public benefit corporation, which means that we have a legal obligation to balance the interest of shareholders and stakeholders according to a public benefit. I can summarize it being mutual trust and privacy. We are also a dual-use company, and we got accepted in the DIANA program for NATO, the alliance, the North Atlantic Alliance. DIANA is the accelerator, and we just learned a few weeks ago that we've been selected for rapid adoption in the NATO Rapid Adoption Action Plan. So as I mentioned, the intuition, as you know, you guys, some of you who've been around for a bit can remember the 1993 cartoon where dogs basically pretend to be humans. I found the one on the right quite amusing. We are now in 2025. We still have the same problem, except that now we have agents pretending to be bots, pretending to be humans. And so obviously this tongue-in-cheek cartoons clearly shows that we still have this underlying problem of identity on the internet. And we should not be surprised, and on the web in particular, we should not be surprised because the web is really architected around domains and around trust in the IT teams that manage the domains. So we have insiders, trusted roles, and everything else aside from the domain is basically a resource within a domain. So it shouldn't be a surprise that we don't have privacy, we don't have confidentiality, we don't have authenticity, because there's always somebody in the middle that can go and tamper with stuff. Regardless of all the security measures that we take, encryption, PET, and all that, we have that problem that remains. And so it's important to understand that that problem just compounds. And over the past decade or so, we've seen that every system now is no longer in isolation. Everything connects to everything else. Our information is flowing everywhere. We have APIs for every system. And now the attack surface just becomes unmanageable because we have insiders and attackers, of course, across the board. So the way we approach the problem, and we imagined two entities, and an entity for us is a person, an organization, a physical thing, an IoT device, or even a digital thing, a digital asset, a file, a firmware update, whatever it is. And we figured, how do we establish a relationship between those things? How do we enable a connection, a relationship between entities at global scale, not within the domain, removing what's in the middle and doing it in a zero trust way. Zero trust being never trust, always verify. And because we are now moving into the agentic era, we're going to have agents that are in the loop. So now we have this problem of how do we do this with agents? Actually, you'll see that it helps in the architecture. But the problem now becomes, how do we move data from A to B? And I would say information instead of data, because we want to maintain the provenance and integrity of that information, but across agents without having any place where the chain of custody is essentially broken. And so the solution, in fact, lies in using confidential computing technology. So you heard Mike earlier today. This is a quick shout out for the Confidential Computing Consortium. You guys should join if you haven't joined yet. But really, to summarize the properties that confidential computing gives us, it gives us three foundational properties. We talked primarily about the first two, the fact that it protects information and code in use through encryption at the CPU level, at the chip level. The second is the remote attestation property, which enables that remote verification, which is the zero trust element, which is critical for assurance, for having assurance that the properties are indeed what you expect them to be. And the third one that is less understood, but that is also very transformational, is the fact that those confidential computing chips have now full entropy random number generations within a trusted execution environment. So this is important because that means you're going to be able to do decentralized cryptography. You're going to be able to generate keys within the TEE. And this gives you the layers, the mechanism by which you're going to be able to build what we call entity-centric security. Remember, the entities for us is people, organizations, physical things, digital things. You start by verifying the chips. That's the remote attestation capability at the chip level. The chip then gives you measurements about the code itself or the process that runs at that moment in time. So you can verify that. And then because we have true random number generation, we can put cryptographic libraries there, generate keys within the secure environments, and then we can generate keys for each and every individual entity that will be mapped and managed within that infrastructure. And so let's try to come up now with that architecture that eliminates the human in the middle, or the IT in the middle. But the first step, as you can anticipate from the identity challenge that I put in the beginning, is that identity servers, identity systems should be built in confidential computing machines. It should be pretty obvious, identity is the cornerstone of all of cybersecurity and primarily of zero trust. So the first thing to secure is the identity system. So your entity should be enrolled, identified, and should authenticate itself to its own, or to a workload, to a process in a confidential computing environment represented by hexagons here. We call them agents because that workload will act on behalf of the entity and will be able to do that in a cryptographically strong way because it will generate keys that are unique for each individual entity. So entity A does that with its own protocols and its own agents that deploy there in a confidential computing environment. Because it has keys, it will be able to encrypt the information for entity A, and entity B should do just the same. Remember that entity B could be a different thing. Entity A can be a human, entity B can be the car, or can be a nuclear power plant, could be an organization. All that we're trying to do is establish a connection so that they will be able to exchange information and secure it at both ends of the connection. So that, of course, does not solve the connection between the two. But as I told you, what we want is the assurance, not just believing that the properties are there. We want the properties to be assured. And for that, we're going to deploy the remote attestation and verification capabilities of confidential computing. So we're going to put another workload, another process that's going to run in another TEE that's going to verify the agent. And so we call that a verifier in the terminology for confidential computing. So a verifier workload will verify the agent, and that's all good. But of course, the question is, who verifies the verifier? So great, we're just going to use the same principle, and we're going to deploy another workload that's going to verify the first verifier that verifies the agents. So you're going to say, okay, Manu is like being silly right now because this still doesn't solve the problem of interconnecting things. And we still have a verification problem. But as you guess it, the next step is actually pretty intuitive. If we introduce a shared verifier that verifies the other two verifiers that, recursively and hierarchically can then verify all the way down to the agents, now we have something because we have a path that goes through trusted execution environments. They've all been verified. Let's leave alone the shared verifier at the beginning. We'll see how we solve that. But what you see is that you have a path now through which you can actually do a verified, trusted key exchange so that now agent A and agent B can have their own unique link key, as we call it, and they can each keep a copy of that link key in their encrypted information space for themselves. And each link key can be unique for each entity. So even if the agent is representing millions or billions of humans, for instance, entity A has a unique keychain managed by agent A, and then has a unique link key with B to talk to entity B. And so that gives you this pattern there. Of course, if you can do it with two, you realize that you've actually solved a problem that enables you to chain those things. And now you can create chains of custody where if you repeat the pattern between 2 and you extend it to 3 and 4, you can create complete chains of custody of command, control, and communications between any two entities. And that is in contrast with what we have on the web today, where, as we said, we can't verify any of the systems that we have. So we cannot have any assurance of privacy, authenticity, and confidentiality anywhere. The reason why this approach must be thought of globally is that it's enough to have just one link in the chain to not be verified, to lose the assurance of authenticity and privacy across the system. So we had to have an approach that would be global. And so to summarize, the principle here, we need to add one more thing, is that entity A and entity B need to be able to be introduced to one another, be known to one another. And so for that, they're going to exchange aliases. They will be able to register aliases in the shared verifier. The entity B will be able to resolve that alias. They will be able, as we said, to exchange public keys. And this should remind you of an existing piece of infrastructure that did this quite well for domains, but of course didn't do that for any other type of resources. And that's really an architecture on the web that the DNS and the certificate authorities in the mesh, what we've developed and what we've deployed is what we call the universal name system, which is a registry that enables a tamper-proof registry that is built on that construct, and a universal certificate authority that automates key exchange and issuance of certificate to all the different processes and actors within the system, all the way down to the agents, so that all cryptography is fully automated across the entire infrastructure. Because each agent can have its own keys and can encrypt its own information, manage essentially you can encrypt and manage their own ledgers. So each agent can have a private cryptographically strong ledger, completely tamper-proof. And then finally, because we can deploy more of those agents without going to the details on how, we can enable zero trust computing where any organization will be able to deploy their own agents on this new infrastructure. The way it looks is that if you remember the pattern of just a few verifiers, this pattern is fully hierarchical and recursive, so you can chain that all the way up. Yes, the initial verifier at the top, we call it the global trustee or the global verifier, it cannot be verified. It must be operated and trusted by a coalition of corporations or organizations, very much like the global DNS servers are managed by a handful of companies in a public-private partnership. But otherwise, you can scale out by exchanging chains of trustees or chains of trust all the way to the edge of the internet across the entire world. And then at the end of each one of these chains, you can deploy those agents. Each one of these agents will have their own private ledger. And because each one of these agents have been globally verified and exist on a chain of verifiers, all of them will be able to exchange keys. So you'll be able to have direct pairwise secure connections between any two of them. If you take this diagram and you fold it onto itself, you end up with a diagram that looks very much like a mesh. It is indeed direct pairwise connections. And then you have these entities that I mentioned in the beginning. People, organizations, nations will be able to be represented as entities. IoT things like cars or plants or whatever. And then AIs themselves, AI agents exist in and of themselves, and then will be able to plug themselves in that infrastructure to interact with any other type of entities. And the properties that you get is not only privacy, but it's really the provenance, integrity, authenticity. You can build reputation, auditability, and of course, you have confidentiality and privacy that were built in by default. Another very interesting property is that because each agent has its own keys and can encrypt its own information, this is a snapshot of the content of any of the databases of any of the agents. No human has access to any information. Only the rightful agent has the right keys to access the right information. Even the identifiers are completely random or pseudo-random and cryptographically uncorrelatable. So you have complete decorrelation. You cannot recorrelate information outside of the infrastructure. So we actually believe that this is the optimal blueprint because it is the least trust technically possible, because every single, with the exception of the initial verifier, that of course cannot be verified, otherwise there would be another initial verifier. But with the exception of the global verifier, all the entire infrastructure is verified at the chip level. There is no layer underneath that. And because everything is encrypted with keys that are only managed within trusted execution environment that have been verified, we also believe it is the smallest attack surface that is mathematically possible. And we're talking about orders of magnitude better security, by the way. So the first application that we built is messaging. Yes, it's messaging. It's on top of this mesh infrastructure. You can actually go and play with it. I'll give you the URL in a second, m.sh. But although it looks like a conventional messaging application, underneath it, it's exactly the same security model, and you can connect all types of entities that will be able to interact with humans and with AIs through that universal messaging type infrastructure. To interact, I know that some of you will say, well, we need to rip and replace everything. That's not the case. The mesh is indeed a very small infrastructure today. There's not a lot of people on it, but just like the web started with one server 30 years ago, it's somewhere at CERN. The mesh is small, but we have bridges that enable interaction with the web. We have an OpenID Connect identity provider service built in, APIs to call back into the infrastructure. We have multi-factor authentication built in, credentials, and then we'll have a bunch of capabilities that we are developing, like mesh drive, essentially mesh memory, and other things that will come later. So that's it. This is not just a science project. This is actually deployed in production. So if you guys want to go and play with it, it's very early stage, so it is not fully unrun. It is in production. It is redundant. It should be stable, but we may run into issues. So don't put anything too confidential or too critical. But you can go right there. You can send me a message. Use my email address to find me, create a space, and then let's get on the mesh.
Very good.
Happy questions.
How about now?
There we go.
Oh, sorry about that. Yeah. So, thank you, Manu. We see there's a question from Nitu. Any published papers on how HSM KMS evolve around this ideal solution?
It's not officially published yet, but you can reach out to me. You have my email address at manu@hushmesh.com. I'll be happy to share a internal document that we have. The interesting thing is that once you have every process being able to generate its own keys and then being able to be verified by a parent process, you end up with a built-in automated decentralized HSM by design. So we don't have, there's a piece that I did not discuss because it would have taken too long and it's too mathy. But there's basically the mesh functions by uniting identity and cryptography so that you don't have a separate HSM or a separate key management system. It is because, in fact, the identifiers that are managed within the mesh are cryptographic themselves that we can have automated chaining that chains back all the way to the identity of the entities that are represented in the information space. So we don't have a separate HSM. We don't have a separate KSM or KMS. It's all built in and it's fully automated. So the mesh has its own, as I said, decentralized certificate authority, its own keychain management. All of it is automated at the infrastructure layer.